Hello, everybody. We welcome you today at tinyML Meetup Talk. This event is the second event in tinyML Meta group that we launched in Grenoble, France. The main objective of this event is to support the ultra-low power machine learning community and, of course, to expand the tinyML ecosystem. My name is Irina Sizova. I'm the organizer of today's tinyML Meetup discussion. Traditionally, at the beginning of the event, I would like to say a couple words about the sponsors. AON devices, ARM, DeepLight, Edge Impulse, EMSA, GreenWaves Technologies, Latent AI, HOTG, Imagimob, Maxim Integrated, Kixo, Qualcomm, Reality AI, Seed, SensiML, SynSense, Syntian. All those companies contributed financially to this initiative and helped to make this project real. Now, a couple slides about tinyML events. So the next event that is going to be online in Asia in November 2nd. Please register and join. It's always very interesting for networking and to participate in the discussion. Another event that was launched already, which is tinyML Vision Challenge. All those developers that are participating in this challenge, please go back to the page in October. The winners will be announced in October 5th. So now I'm ready to present our guest speaker and the moderator of today's discussion, Alexandre Valentian, who is currently pursuing the development of Bioinspired circuits for AI. And since 2020, he heads the Systems on Chip and Advanced Technologies Laboratory. Now, I would like to open the floor to Loïc Liétard, a co-founder and the CEO of GreenWaves Technologies, who initiated this tinyML meetup talks in France and who really believes in the power of open source community. Loïc, please, the floor is yours.
Thanks, Irina. Good afternoon to all, and thank you for joining our second meeting. There were more than 100 of us attending the first meeting, which was a broad overview of the state of the art of tinyML in terms of research, application, and hardware. After the meeting, we ran a survey, and you told us that you were interested in hearing more about hardware first, a bit to my surprise, I must say, and then about applications, software tools, and low-power sensors at the same level. All in the context of tinyML, of course. And we will be covering those topics in the next meetings. Today, we are delighted to have again a great attendance for the talk of Alexandre on frugal hardware. Alexandre, please go ahead.
Thank you. Thanks for the introduction and for having invited me today. So now you should see my screen, full screen. Is that okay? Yeah. So today I'm going to talk about how to design a power frugal hardware for artificial intelligence, and especially the things I'm looking for several years now, how to use the Bioinspired as a way forward to lower power circuits. So I think I'm not going to learn you something today by saying that right now, most of the AI applications are running in the cloud. You all know that already, obviously. And that's obviously because it's convenient. Processing power is available. So you do learning in the cloud, for which you need very large data sets and a lot of computing power. And then once learning is done, it's very convenient to use the same hardware, the same assets for performing inference. But as you may know, obviously, we already see a trend coming. More and more people are looking at doing the inference at the edge, on chip, and for a number of reasons. The first reason might be the safety of operation, because you might not want to constantly rely on a wireless link for making a decision. Another reason might be the latency of decision making. Obviously, when you do make the decision locally, it's done much faster. Another reason might then be privacy, because you might want to keep your data local to keep them private. I know it's a European focus to deal with privacy. It's not the same thing in Asia, but obviously. But most surely it's about power dissipation, because when we'll have thousands of intelligence devices surrounding each of us, obviously the cloud-based AI scheme will not be sustainable in the long run. So it will not be able to sustain the load, and part of that load will have to be offloaded to the edge devices themselves. And the ultimate evolution to that trend is to perform even the learning on chip at the edge. When we have autonomous agents, we'll want them to adapt to the environment, so to learn from experience and thus exhibit lifelong learning abilities. So we learning on chip. Obviously, there might be some kind of cooperation with the cloud for sharing experience between agents. So let's start with first performing inference at the edge. So what's the main issue to be solved? Obviously, the main issue is the energy dissipation. And in data-centric applications like AI, most of that energy dissipation comes from moving data. As you can see on this drawing, so if we make an external memory access, it costs in the range of nanojoules of energy. And if you compare that to operations done on chip, so even considering 32-bit or 64-bit floating point operations, it lies in the range of picojoules. So it costs hundreds of times more energy to move data than to compute on data. So the key here is to avoid moving data too much. So the trends in computing we see right now are the following. So first, since you want to avoid moving to large data, you can start by quantizing data, so using reduced precisions for the weights and for the activations. Thanks to that, you have a smaller memory footprint, you have lighter operations in terms of energy consumption. Then you can go, so it implies not considering 32-bit floating point operations, but maybe 8-bit integer or 4-bit or even binary operations. Then you can go up to even considering variable resolutions or precisions in your circuit. So you can have lower precision in the convolution filters, for instance, and a higher resolution in the output classifier. And obviously you want to exploit sparsity for having less operations, so a sparsity of weights and sparsity of activations as well. So you save on operations, you save on memory accesses. On the memory side, so you want to increase the storage efficiency, and that amounts to have denser memories on chip and memories which are very close to the compute engines, again, for avoiding too many too many memory accesses and on long ranges. So for that, you might implement weights using non-volatile memories, which are very dense, can be integrated in the backend of line. And for the intermediate results, you can use SRAM or embedded DRAM for density. And the ultimate trend of this, having the memory very close to the compute engines, is to even perform the computing inside the memory. So it's the in-memory compute paradigm. So it can be implemented either in SRAM or embedded non-volatile memories, and in a digital or analog manner. More and more people are considering an analog in-memory compute in arrays of resistive RAM memories, for instance. So maybe let me give you a glimpse of what in-memory compute is, so that's the digital version of it. So on the left-hand side, you have a classical von Neumann architecture in which you have the CPU, which is separated from the memory. And inside the CPU, you have the ALU, the arithmetic and logical unit, which does operations such as addition, multiplication, division, and so on and so forth. And that separation leads to a large data movement, because when you want to perform a computation, you first have to fetch data from the memory, do the computation inside the ALU, and then write the result back into the memory. In the IMC paradigm, you have parts of the arithmetic and logic which is located inside the memory, so you can execute part of the instructions directly inside the memory. So obviously you have lesser memory transfers, and the second benefit is that you can do operations in parallel in your memory. It's kind of a vectorial ALU, if you will, and so you have a large speed up of your operations. For instance, if you consider an 8-bit micro-operation, you have a speed up of 256x, and at the same time, you have a reduced energy dissipation by a factor of 9x. So that was for the activations. For the weights, as I said, you can implement them using non-volatile memories. It's done more and more nowadays. Well, that's because it's very convenient. The weights do not change often, and you do not have to reload the weights each and every time you power up your circuits. And as I said, it can be very dense, and in the medium term, it can be implemented above the CMOS layers, so in the backend of line, which is convenient as well. So at CA, we are working on memory technology for those weights. We have demonstrated that it's scalable to below 20 nanometer CMOS, so it's very well scalable, much more than MRAM, for instance. It can be multiple valued. We can store up to 4 bits, so with different resistance levels. And we have a technology roadmap for integrating, for increasing the density even more by a factor of 10x, for instance, moving from 40F square area to 4F square, thanks to backend of line selectors. So you do not have access transistors anymore, but a selector which is in series with your resistive RAM, so it's very dense. I'll give you just a few examples of what we can do with such a technology today. So we have network topologies, which are very often used for benchmarking in AGI applications, so like ResNet 50 and YOLOv3. So you see it amounts to between 75 and 100 megabytes of weights. And with the current available technology, it's only, I would say, 15 to 20 square millimeters of area. So it's already integrable on chip. And you can imagine that with the future technologies, it will be even denser. So we'll have even more memory on chip or reduced by area used by the memory, obviously. So when we now look at the learning on the edge, so obviously it shares all the challenges we've seen for the inference application case, but we have additional challenges due to the learning phase itself. That's because for running the gradient descent algorithm, so in the backward pass, for calculating the gradients of the different layers, we have to first store all the activation results during the forward pass. So that's a lot of memory, and you might not want to do that, this backward pass for each input, but for a batch of inputs, if you do not want to have too high energy dissipation, or you do not want to cycle your weights too much. And again, for this YOLOv3 example, a batch of 20 images would require 800 megabytes of memory just for storing the activation results and calculating the gradients. So obviously that such an amount of memory can be put on chip. It most probably will be DRAM memory for density, and it will be off chip. But the issue we've seen with off chip memory accesses is that it dissipates too much energy because of the long wires and the capacitance associated. So one way of circumventing this is going to 3D technology, in which we'll have much shorter and larger memory accesses, if you will. And again, we have technology roadmaps in the industry as well for reducing that pitch and having very tightly coupled memories with the compute engines. So you see, we can go even down to 1 micron pitch, which is very, very fine thanks to hybrid bonding, wafer on wafer. So yeah, so that might seem like a kind of long term, but what we envision is having for very powerful edge AI applications, having that multiple implementations in which we have this parallel architecture with one tier made of generic processing engines like CPUs for handling exotic neural network layers, and we have one tier of in-memory compute in SRAMs for energy efficiency. Then we have one tier with embedded NVM for storing the weights, and we might even add DRAM on top if we want to enable on-chip learning. So I agreed, it's not really tiny, but that's the way it is. I think that we all know that the complexity of neural network topologies just keep increasing over time. So yeah, that's going to be some future applications running at the edge. But still, when we compare with what engineers do achieve with silicon technology, with what nature achieves with, let's say, bio or wet technology, we see we are still far from what nature achieves. In this figure, you have the raw compute power, and see it's a logarithmic scale, so it's in gigaops. So here you have 1 teraops, 10 teraops, and so on and so forth. And on the y-axis, you have the computing efficiency in terms of gigaops per watt. Again, it's a logarithmic scale. You see the different implementations from the academic world, from startups, from large industries. And when you compare their energy efficiency to the one of a bee brain or a human brain, you see that we are still orders of magnitude below what nature achieves. So it might be kind of a good idea to take inspiration from biology. So what does that mean, be bio-inspired? Well, we'll have a look at how the brain is made and how we can derive specifications for circuit design, basically. So first, we see that the brain is massively parallel with 10 to the power 11 neurons and 10,000 synapses per neuron. And by the way, you know, synapses are very close to neurons and very much intertwined with neurons in a 3D manner. We don't have all the neurons on one side and all the synapses on the other side. It might be foolish when I say it like this, but it's the way GPUs are made today with the processing engines in the middle and the HBM memories on the sides. So that means we need a very high density storage very close to neurons, and one way of achieving that is exploiting non-volatile memory technology, for instance. We see that part of the processing is done by the synapses because they do wet inputs, so we need some kind of computational storage. Again, it can be achieved thanks to NVM memory. The computation is analog. Actually, the soma, so the heart of the neuron, it accumulates synaptic currents, so it can be seen as a capacitor, right, with a threshold. So it might be a good idea to design an analog neuron. But on the other side, the communication is digital. It comes in the form of spikes, which are unary events. It's not even binary events. It's not 0 or 1. It's you had an event or not, and it happens to be very robust to noise. So that's why I think nature chose this mechanism for communication. So why not use spike coding? And the added advantage is that it's a very sparse coding, by example. And we know that we just want to exploit sparsity even in the coding. So yeah, we made a proof of concept following those lines a few years ago. So exploiting spike coding, resistive RAM synapses for basically just exploiting physical laws. You see Ohm's law for weighting the inputs and Kirchhoff's law for adding the various inputs. And analog nuance, which can be seen as a capacitor with voltage comparators at the output. And yeah, so since it's a proof of concept, we tackled a very simple problem, which is the MNIST classification. It's kind of the hello world of neural networks. Everyone does that at the beginning. Everyone considers doing MNIST classification. So we want to classify digits with a grayscale encoding of the pixels. So we consider a rate code here. Where the brighter the pixel, the higher the frequency of spikes at the output. So we have an encoding layer. So this is basically a rate code or frequency code. Again, proof of concept, so a very simple topology. We considered only a single fully connected layer. So we have 10 digits, 10 output nuance, and each nuance sees the entire image. And it has 144 synapses, 12 to the square. So how are we going to learn that for just writing the weights on the circuit? So we could have considered Bioinspired rules. We know there are unsupervised rules which were proven by people who were looking at how it's made in biology, but the problem is that it can only optimize local cost functions and not global ones. So if we later on consider deeper networks, that would give poor results compared to the gradient descent algorithm. So decision was made to use an offline learning strategy based on gradient descents. So learning in the classical domain and then transcoding into the spike domain. And for that, basically, we needed to have a mathematical equivalence between the two worlds. So the classical coding domain, basically continuous values, and the spike coding domain with events. So for that, for the classical domain, we considered a hyperbolic tangent activation function, which looks like this. See, looks like a sigmoid. And so we made an approximation of this S shape with those straight lines. So here you see the saturations in terms of output frequency or output value in the classical domain, if you will. And for implementing that saturation, we introduced a refractory period for the neuron. So the maximum firing frequency of the neuron is 1 over this refractory period, right? And the same for the negative values. So we have positive spikes and negative spikes. And for the slope in between, it's determined by the threshold of the neuron, so the positive threshold and the negative threshold. So it's the way the receptive fields of the different neurons look after the learning phase. So here you have the neurons coding for the digit 0, digit 1, 2, and so forth. And in green, you have the excitatory synapses, in red, the inhibitory synapses. So you see, for instance, for the digit 0, the neuron is very much excited by this shape, this loop, right? And is very much inhibited by activity in the middle. And for the neuron coding for digit 1, it's the opposite, right? It's excited by the shape and inhibited by activity on the outskirts. So now that we have those receptive fields, the question is how we're going to implement those values using resistive RAMs. So at the time, we only considered using resistive RAMs in binary mode. Since then, we know that we can use them with multiple values. So we had to consider how many resistive RAMs we're going to use for implementing the values. We made experiments, quantization experiments, by the way, and we've seen that we still have good results with a reduced rate range from -4 to +4. So we had to encode 4 values with a sign bit. At that time, we were not too confident to put the sign bit on a single resistive RAM. So we said maybe we might consider having a majority voting with 3 resistive RAMs. So in the end, we said, okay, we're going to do much simpler. We by convention determine that one side of the synapse is for the inhibitory side and the other part is for the excitatory value. So for instance, HRS means high resistive state and LRS low resistive state, so high value or low value. And it's an example of an implementation coding for the value +2 because we have 2 devices in LRS state on the excitatory side. So that's the way the synaptic matrix looks like. So it's a synapse here with 8 1T, 1R devices or scheme. So it is the access transistor for each resistive RAM. As I said, since then, we can also make the decision to use OTS selectors, so devices looking more like bipoles. And so, yeah, we have this array of different synapses here. So now looking at how we implemented the analog neurons. So as I said, it's basically architected around a capacitor, which in this case it's 200 femtofarad. On the output, we have 2 voltage comparators. 2 because we need 2 thresholds, a positive threshold for emitting positive spikes and a negative threshold for emitting negative spikes. And for reasons of mathematical equivalence, we need to have special reset mechanisms, reset paths. When the neuron fires, we do not reset the membrane to logical 0, for instance. Those are the different voltage levels we do have in the capacitor. So with logical 0 being between 0 and 1.2 volts. So here 600 millivolts. And we have the 2 different thresholds, negative threshold and positive one, and the different increments we can have in the capacitor. So this was fabricated on base wafers from ST Microelectronics, 130 nanometer, and the resistive RAM post-process was done at the LAT between metal 4 and metal 5. You can see here, and on the chip micrograph, the synaptic array is here, and with the analog neurons here. So this worked hopefully, and we made a lot of electrical measurements on this. So you see the classification accuracy. So it's not large for MNIST classification, obviously, but keep in mind that it's only a single fully connected layer. And when we compare that to simulation, we see that obviously viability is impacting our results. So that's something we considered afterwards. But still, thanks to the sparseness of this coding strategy, we have less than 1 event per synaptic connection, so it's very sparse. And we can classify an image dissipating only 25 nanojoule of energy. And that's at least 5x less than classical coding. And that's not even considering that we do not have external memory accesses in this case. So it's quite energy efficient. So it's not only a test chip, but we've made a demo with this. It's available in our showroom. So we can now play with it, draw digits with our finger on a tablet using the drawing zone. This image is then converted into gray levels, 12 by 12 pixels. So that's done by an FPGA, and then the FPGA emits spikes to the circuits, and then it sends the output spikes of the output classifier nuance, and then the result is written on the tablet. And this was presented a year ago and in IEDM, or 2 years ago, by the way. And so in the meantime, we have considered improving our design by going to much scaled technology. So you see there's a large gap in terms of area between 130 nanometer CMOS and 28 nanometer FD-SOI. So the area was divided by between 20 and 30x, and the energy per event by 10x. So that's only technology scaling, but we even considered using multiple values resistive RAMs. So instead of having 4 different resistive RAMs for the 4 different synaptic weights, we now have only one in which we can have multiple resistance levels for coding level 1, level 2, 3, and 4. So we have now, instead of in total 8 box RAMs, we have only one multiple value for the absolute value of the weights, and one single cell value or resistive RAM for the sign. And so when we consider the scaled and multiple value implementation of our design, we see it compares very well to the state of the art. And just keep in mind that we can now implement in an analog manner 2.3 million synapses per square millimeter, which is quite large, and the energy dissipation is very good as well. But still, as I mentioned, we had this issue with viability, obviously. So what we've seen is that analog mixed signal is very good if you want to have very large, very shallow networks. But obviously, if you want to go to deeper networks, it's not tremendous because errors would add up. So you have 2 solutions. One is doing online retraining, but that's not an industrial solution, but it would be too time consuming. And the other solution is to shoot for digital implementation, which is much easier to handle. You can have cycle accurate simulation with your circuit, for instance, for debugging. So that's what we considered for deeper networks. And we needed deeper networks for use with a LiDAR for doing operations such as detection, classification, segmentation. So you see it's a much more complex task, and those tasks are implemented with topologies looking like a U. So it's what we call unit topologies, in which you have convolutions and deconvolutions operations. So here most of the operations are convolutions. And so for this second circuit, we just considered those convolutions operations first. So we have a multicore implementation. So it's in 28 nanometer of this. So again, with resistive RAMs for the synaptic weights. Multicore, so you see here the 8 different cores and details of each core with the synaptic weights, the SRAMs for the soma potential, so the membrane voltages, and logic for updating those membrane voltages. So obviously you see that compared to a mixed signal analog implementation, we are much denser with a digital implementation. On only 3 square millimeters, we have 130 k-nuance and up to 75 million equivalent synapses because we share weights between synapses. And the energy efficiency, we did a lot of effort on this, and it's now below 1 picojoule per synaptic events. So it's can kind of good value, by the way. So in conclusion, obviously, you see first we'll have accelerators, and now you see a lot of different accelerators, either classical coding, spike coding, analog, or digital. So for inference first, and then because application will need that, we'll have on-chip learning as well. In both cases, the main challenge is to reduce data movement as much as possible. So we'll have a bunch of solutions for this, computing in memory, memory technologies for having those memories very tightly integrated with the compute engines, and eventually through the integration if we want large memories to be available. But anyhow, all those solutions do apply as well to more bio-inspired solutions, with its main advantage being the coding, which is very sparse. So thank you for your attention, and I'm open to questions.
Thank you, Alexandre. Fascinating. What is fascinating is how machine learning is reopening the space for innovation in computing architecture.
Yeah, it's a new model of computation, basically.
There is a first question from Rajiv. What is your view on embedded MRAM as embedded non-volatile memory? Is it fast? It is fast like SRAM and readily available in the fab, sorry.
Yeah, so MRAMs, yes, this is currently available in industrial non-volatile memory technology, but we do know that it does not scale well in finer technology nodes. So usually it's available at 40 nanometer or 28, but below that, like maybe 12 LP or those kind of nodes, we see that foundries like TSMC or global foundries will resort to different resistive RAMs technologies, either CBRAM or PCRAM or FERRAM or whatever. So yeah, I think it's most probably a scaling issue that goes with MRAM.
Okay, other questions? No, so if not, maybe waiting for the question from the attendants, I have a few. Oh, sorry, Agustinus is, how does your approach compare to Mythic's AI's approach?
Yeah, so I would not like to compare to what others do, because you know, everyone will say that their approach is the best, obviously. I don't think that there's no one size fits all, right? So in some applications in which you'll need very deep networks, you'll need full digital implementations, and maybe resorting to temporal coding instead of red code, or maybe combinations of a red code with a classical coding. We do see that right now more and more people are considering encoding layers at the input and decoding layers at the output. And in other cases where you are very tightly integrated with a sensor, it can be an ultrasound sensor or an image sensor or whatever, maybe you'll need to have more analog mixed signal implementation with maybe online learning mechanisms as well. So it's very difficult to compare, and now there's too much accelerators on the markets.
Alexandre, there are many people write if you can share actually the resource presentation and references that you mentioned here. I told to everybody that the recording will be available on tinyML website, but it's a question you can. Okay, so to
case numbers start to go down and go back to where things were, like in the.
Sorry. Okay, but this material will be shared, obviously.
Okay. So waiting for the question I have, this is Loic. I have a couple of questions for you. First of all, have I understood well that you said incidentally that analog computing is a no-go for industrial production, for volume production?
No, it depends. Again, it depends on the applications and your needs. There might be applications in which you need to adapt to the situation or to adapt to your sensor because you have variability in the sensor or shift in parameters or whatever. So in those cases, you might want to implement online learning mechanisms for adaptation. And in which case, variability is not an issue because it will be handled by those built-in mechanisms. But if you're shooting for very deep networks for inference only, and you just want to write your weights at electrical wafer sort, and then you're done, obviously it cannot be done economically using analog mixed implementation. It has to be fully digital. So it's not that it's not tailored to industrial application, but it very much depends on your needs.
So, which means that you, as part of your research, you have envisioned how to test in mass production such chips.
Yeah, so fully digital is.
No, in analog. In analog.
Yeah, we need some kind of DFT and BIST of the analog parts, and then maybe mechanism for dealing with faulty neurons and so forth. But very much like we have BIST for memories or for PLLs.
Okay. So there is other question coming from the attendant. Georgios is, it is usual for the ML models to be compressed with quantization and other methods. What are the restrictions in the model design in compression when in-memory computing is used?
I think there's no limitations due to IMC. By the way, you can have very different IMC implementation mechanisms. It can be down to binary networks in which it's only XOR operation done in the memory, so very simply. Or if you have higher resolutions, you'll need to have MAC operations occurring inside the memory, which is again feasible on the periphery or even in an analog manner, just doing matrix multiplication in your memory. So I don't think there's any limitation because of the IMC scheme.
Okay. Jerome is asking, what are the other labs that are involved in, I understand, similar research in the world?
A lot, but if we stay in Europe, you have at least the University of Zurich, obviously, with several startups, by the way, and you have CSEM and a bunch of others. And worldwide, I'd say there are too many to be named like this. But so to be honest, it's still research projects, right? Because there's not a single industrial application of spiking neural networks right now. But I think it's going to change because what we're lacking from up to now was dedicated sensors, even the sensors, and we see them coming like image sensors from Prophecy or other companies. So it's going to change.
Okay. Question from Rajalakshmi. I apologize if I didn't pronounce your name properly. Can you elaborate on image classification implemented on the Zinc board?
Yeah, so in this demo, the Zinc board was just used for doing the interface between the tablets and the circuits. And by the way, translating, so doing this encoding input, translating the image into a train of spikes using the rate code. So it's just an SPI interface between the Zinc FPGA and the circuit, and we send trains of spikes and read the output of the circuit. So it's just for doing translation between the two domains. But actually, all the classification is performed on the SNN test chip.
Okay. Question from Xavier. Would you say the Bioinspired path for AI is a lively/growing research field, even close to industrialization for some cases? or would you say it's mostly for a few labs looking into it for now?
No, I'd say it's growing. Obviously, I'm working on this. Will not say the opposite, but I don't know if it's close to industrialization. Maybe we'll see products in a few years from now. But yeah, definitely it's growing. And as I said, we should not oppose the two coding worlds or two coding domains, like classical coding on one side and spike coding on the other side. We see now we can do a big mix of both on the same chip with encoding and decoding layers. And we know that depending on which layer you're considering, the sparsity is different. So on very sparse layers, you might want to use spike coding. And actually, we're also working on learning frameworks that can handle both coding strategies at the same time and choosing the best depending on the layers you're working on.
Okay. Question from Ayush is, how can depth analysis for dual camera be implemented? If I understood well the question.
I don't know how to answer that. I'm not an expert in depth analysis using cameras. You mean? No, I don't know how to answer that.
Okay. I have there are no further questions. I have another one. You mentioned rapidly on chip learning. Are there unsupervised learning opportunities in tinyML application? And from Greenway's perspective, we don't. I mean, it's always supervised. And if not, how would you do supervised learning on chip?
Yeah, so we do have both, I think, in terms of application, unsupervised and supervised. Unsupervised being you might want to learn a time series of vibrations, maybe for determining whether we'll have a faulty machine or whatever. So for doing predictive maintenance, and you can have supervised learning as well. For instance, we have solutions for incremental learning in which we have autoencoders for deciding whether we already know that class or not. And those autoencoders are learned on a supervised manner, but you do not need to supply labels to the circuit. So it's an auto-supervised learning, if you will. So
you define rules for what is something that doesn't belong to a class but is close enough so that it can become part of that. Is that right?
Yeah. So the system can determine whether it already knows that class or not, and if not, learns a new class, and then we can give a name to that new class. But we do not supervise the circuit in terms of learning specifically that class.
Okay. Question from Martin. How much flexibility do you currently have in the structure of the neurons and synapses? How do you see this flexibility being achieved?
So yeah, it's going to be achieved thanks to a network on chip. So obviously being Bioinspired means you have very large fan-ins and fan-outs like in the brain. Obviously, the more flexibility you have, the higher power dissipation. So we are considering both some kind of hybrid architectures in which we have one part which is fixed and another part which is programmable and much more flexible. But yeah, you can do that. Yeah, you can have flexibility thanks to a NOC between computing clusters, and you just.
Maybe I'll add to Martin. He belongs to Greenwave as a disclosure, and our experience is as we go to the path that you mentioned. You are, as you mentioned correctly, you are reducing the energy efficiency, and ultimately we are so far, but we are far less advanced in terms of research than you guys are. The benefit that you are getting from the inner compute architecture is lost when you try to make it generic enough for real life.
Yeah, I agree with that. Yeah.
Okay. It's a lot of, I don't see any other research, other questions, sorry.
And it's perfect
time.
timing to finish our today's talk. Let me again say a couple of words about the sponsors, or at least name them. So ARM, the software and hardware foundation for tinyML. DeepWhite, we use AI to make other AI faster, smaller, and more power efficient. tinyML for all developers. This is, I think, Edge Impulse. Yes, EMSA, the I in IoT. This is a Green Waves, enabling the next generation of sensor and hearable products to process rich data with energy efficiency. HOTG, distributed infrastructure for tinyML applications. Latent AI, adaptive AI for the intelligent age. Maxim Integrated, enabling edge intelligence. Kixo AutoML, automated machine learning platform that builds tinyML solution for the edge using sensor data. Qualcomm AI Research. Reality AI, add advanced sensing to your product with Edge AI tinyML. SensiML builds smart IoT sensor devices from data. SynSense, Sentient. That's it. Thank you very much, guys, and have a great evening or morning. Take care.
Or night, maybe. Thank you. Bye-bye.
Next time.
Bye-bye.
Bye-bye.